Okay, in this video, I'm going to talk about the perceptron model, which is a very simple model for classification tasks, which people don't really use in practice anymore, but it will be extremely important for providing intuition about how different types of more advanced models in machine learning, and in particular models for classification work. Okay, so before we get started, before we dive into the perceptron model, I think it's important to define at least 3 terms that we will be using repeatedly. So first, we'll be talking about feature vectors. So these are really just a row of input variables. We call that X. And that's basically equivalent to the independent variables that we often talk about in econometrics and statistics. Then we will be talking about a lot about a weight vector, which is a set of model parameters. And that's basically equivalent to coefficients in econometrics or statistics. So that could be beta 1, beta 2, beta 3, etc. And then finally, there is the bias term, which is the model intercept. So we call that W0 or W0. So that's equivalent to the constant term beta 0 in statistics or econometrics. Okay, so before we talk about the perceptron learning rule, how we can use the perceptron model to classify a given target, we should talk about the artificial neuron, which is basically constitutes the fundamentals of the perceptron model. This artificial neuron, you will also be if you at a later point work with neural networks, these neural networks fundamentally just consist of a lot of these neurons. So what are these neurons? So these artificial neurons are fundamentally inspired by the biological neuron. So what we have here is an illustration of the McCulloch-Pitts neuron, it's called. So what this is basically, this is a simplified illustration of how the biological neuron works. I don't want to go into detail with this because I fundamentally don't know anything advanced about biology, but the idea here is that the biological neuron, it takes an input signal, and then it fundamentally processes it, and then if the signal is strong enough, it fires, basically it gives an output. So this is also the fundamental idea behind the artificial neuron, and that's the fundamental idea about how the perceptron model classifies a given target. So you can read more about the relation between the artificial neuron and the biological neuron in the PML textbook. Okay, so what is the model architecture of the perceptron model? So the purpose of this model is that we're interested in making a decision rule that takes some arbitrary input and either output something that's positive or negative. So that's a positive classification or a negative classification. So mathematically, we can define this as a map. So this is phi, this is a function. It's a decision function that takes a d-dimensional input, and then it processes it. You can think of it like that. And then it gives us an output that can take 2 different values, -1 or 1. So that's negative classification or positive classification. So phi is a function, yeah, as I said, takes a d-dimensional input and maps it into a 1-dimensional binary outcome. So more specifically, this decision function, it looks like this. So it takes a value of 1 if this set I, which is the input, is the aggregate input, is the net input, we will call it, is strictly positive, while the decision function will give us a negative value if this net input is weakly negative. So this net input, that's simply given by this linear index here, and this is something that you will recognize from linear models, and for instance, when you work with econometrics. So that's simply just a dot product between our features and our weights. So it looks like the following. yeah. So this is what it looks like in practice. So what we have here is the decision function, basically this artificial neuron, and this is the net input. And we can see that we have negative classification as long as this net input takes a negative value, but then from the point when this net input is strictly positive, this decision function gives us a positive classification here. Okay, so we also have an illustrated example here where we have two different target types. We have, say, positive classification and negative classification here. In this case, this decision function takes a two-dimensional input. So there are two different features here, x1 and x2. And in this specific case, classification, or this decision boundary here, does not depend on x2. So we can see that when we have an observation of x1 that is sufficiently large, this decision function, this decision boundary, predicts a positive classification, while when x1 and observed x1 is negative, we get a negative classification here. Okay, or when it's sufficiently small, we get a negative classification. Okay, so when does the artificial neuron, when does that work? So a requirement is that the two target types, they are linearly separable. So that's, for instance, there was a case in the previous example. Here we could draw a straight line between through the data, and then we have a perfect classification, right? That's also the case here. Now the decision boundary also depends on x2. We can draw a line here between these two different types of targets, and then we manage to classify all our observations correctly. That's not the case here. It's not possible here. It's very difficult to draw a straight line here, right? Or it's not very difficult, it's impossible. And also it's not possible here. We could be tempted to draw some kind of a circular object here, right? And say, okay, it's actually possible to separate these, but they're not linearly separable. Okay, so this is something, if you have a problem like this and you want to apply some kind of classification model to this, you will, in other more advanced courses, learn about, for instance, support vector machine models and random forests for classification, which can help you do this kind of stuff, but you cannot do that with the artificial neuron. Okay, so how do we estimate the model parameters? So in short, the approach is the following. So there are fundamentally two steps with two sub-steps in step 2. So step 1 is that we initialize the weights with some set of small random numbers. These should in general not be 0, but they should be close to 0 and potentially random. Then in step 2, we set some counter k equal to 1, and then we repeat the following until we make no mistake on our training data. So we manage to separate our two target types completely without an error. So for each training observation, I going from 1 to n, then given our previous set of model parameters, so when k is equal to 1, that's just our random guess here, then given our previous model parameters, we try and predict the target that's associated with the features for a given observation. Okay, so we try and predict the target, so we try and classify our object here, and then based on the true class of this target, the features and these previous weights, we update our weights. Okay, so how does this work in practice? So what we do in step 2.1 here, so when we predict the target, how do we do that? So for a single observation, we compute set I. So that's this linear index here. And then we apply our decision function. So that's this unit step function that takes a positive that predicts a positive classification as whenever Z is strictly positive, and negative classification whenever Z is weakly negative. We can also write the same thing up here in vector notation, and we can also, for a full set of data, write it up with matrix notation. So that's not, these two types of notation, they're not really important for now, but I suggest that you take a look at a matrix notation or vector notation when you have time, if you're not comfortable with this way of writing this stuff up. Okay, so this is how you predict y hat. So that's how you make an attempt at classifying the target. So then how do we then update the weights? So that works the following way. So this is basically by definition. So the weights in iteration k is equal to the weights in iteration k minus 1 plus some adjustment or an update. So what is this update then? So this is eta times this prediction error times the features. So eta here is a learning rate. That's a parameter that you will eventually have to set yourself. I don't want to go too much into detail with how this works in practice, but it's a parameter that we will usually set to a value between 0 and 1. So when we make larger adjustments, when we set eta high, we'll also make larger adjustments, but we will also, so we will converge fast to the optimal solution or to the correct solution, but we may also risk missing the correct solution because we're basically taking too large steps when we are adjusting our parameters. I'm coming back to how this works in practice later. So clearly we can see here that when we make a correct prediction here, then this will be 0 and there will be no update. Okay. So in general, when we work with the perceptron model, we will only update for one observation at a time. However, we can also update for multiple observations at a time. Then we will use this type of vector matrix notation. Okay, and this is how the perceptron learning rule can really be illustrated. So first, what happens is that you have a given set of features. This is basically observation, and you have your weights here. Then you use your observation and the different features to compute the net input along with these weights. So that's what you do here. Then you use this unit step function to try and classify the observation. And then if you make an error, you'll go back and update your weights. Then you basically just repeat this process until you make no mistakes. And when you make no mistakes anymore, then you're basically done.